El día de hoy tenemos a un invitado de Filipinas, el profesor Magdaleno Vázquez. Eh, el profesor Magdaleno Vázquez estudió sus undergraduate en la Universidad de Filipinas en química, ingeniería química y ciencias materiales. Eh, Hizo su doctorado en la Universidad de Doshisha, el profesor Magdaleno Vázquez, en Kioto, en Japón. Él es especialista en fuentes de iones, carga y descarga de partículas y la interacción con la materia, y sobre plasma y fuentes de iones. El profesor Magdaleno Vázquez, el día de hoy nos va a dar una charla sobre plasma, interacción con la materia. Bien, I will pass through English, okay? Good morning, everybody. Today we have the speaker is Professor Magdaleno Vázquez from the University of the Philippines in Manila, in Diliman, the Philippines. Magdaleno Vázquez studied chemical engineering and material science in the University of the Philippines, and he studied the doctoral degree there in Doshisha University in Kyoto, Japan. Well, he is the president of the Plasma Society there in the Philippines. He's a specialist in plasma, ions, and the interaction with the matter. Well, he is also the director of technology transfer and business development in office in the University of the Philippines. Well, also, Professor Magdaleno Vázquez, he has been the student of my very good friend, Professor Henry Ramos, the deceased Professor Henry Ramos, who rest in peace. Yes, I was my friend long time ago. And we have, at that time, we have a very nice collaboration with the University of the Philippines. You can share your screen and al público que nos sigue, que me disculpe con la.
Hello.
Yes, go ahead.
Okay. Good morning, everyone, and good evening from the other side of the world. Thank you, Professor Luis, and the rest of LAFMAT for inviting me and allowing me to share our work on plasma surface interactions for value-adding processes. My name is Magdaleno R. Vasquez, and this will be the topic of my talk today. So this is the outline of my presentation. I'll give a brief introduction about our university and our laboratory, some introduction about plasma and how plasma interacts with surfaces. And towards the end, I will give examples, mostly our work and our experience in conducting plasma surface interactions research and summary. So we are based in the Philippines. That's in the Southeast Asian region part of the world. So this is facing the Pacific. But right now I'm in Japan. And our university, the University of the Philippines, is the National University of the Philippines, and it was founded in 1908. And it is divided into 8 campuses and 1 open university. So right now, it offers around 246 undergraduate degree programs and 362 graduate degree programs. I am from the UP Diliman campus, and I belong to the College of Engineering. It's one of the largest colleges in the campus, and in our college, it offers different undergrad and graduate programs. As you can see here, those highlighted are the programs offered by my department. So as mentioned earlier, I'm from the Department of Mining, Metallurgical, and Materials Engineering. And here we conduct instruction and research related to mining, metallurgy, and different materials. Right now, we have around, I think, more than 30 full-time faculty members in the department. So our department has this different thrust when we do our research. So we have eco-materials, materials for energy, responsible extraction technologies, and biomaterials. And interfacing with these different thrusts as well are what we call enabling technologies. And one of that is plasma-assisted processes, as shown here. So this is our lab. So we are the Plasma Material Interactions Laboratory. This was founded 10 years ago. And so far, we have trained and graduated 88 undergraduate students, around 34 graduate students, and we have published more than 60 publications. And in terms of funding, we're able to generate more than 300 million pesos worth of funding. So in the lab, we have this approach. It is similar to what Professor Henry Ramos also did during when they have the plasma physics lab. So we have adopted a modular open systems approach. So in this way, for a given system, we're able to configure and try different configurations of the system without really buying a lot of components or parts. So as you can see in this 2 images, this is the first plasma system that I assembled. So first one is one configuration on the left, and then we just added some parts and we can reconfigure our system. No? For on the left, we have a sputtering system, and on the right, we have a low energy ion source system. So why do we adopt this modular systems approach? So first, everything is custom built. So this gives us modularity and flexibility in terms of assembling and operating the system. It allows us to tweak and adjust our systems if in case we want to try different configurations. I find it cheaper to maintain as compared to buying a ready-built system. It's more affordable, and definitely there will be no vendor lock-in, because if you buy built systems, then usually the warranty and you cannot open or you cannot change some configurations in the system without losing the warranty. And because of the customization and flexibility of our systems, we have more opportunities to learn the different underlying mechanisms involved when we operate our plasma systems and how it interacts with different materials. So this is an example of how we design and build our system. So this was built by one of my students, and she assembled this and then uh, used this. This is a compact magnetron sputtering system. So she used this to deposit different films. So in the lab as well, we are very highly experiential. So students, researchers are heavily involved in terms of doing research, from designing, doing some models, assembling the system, and then, of course, operating and troubleshooting. And then we are also highly collaborative, and our new members or new users shadow experienced or senior members in the laboratory. So in that case, we want to ensure continuity of the skills developed in the laboratory. So these are just examples of the systems that I have designed and built. So most of these are still in Japan. And this is now our laboratory. So we have different deposition systems. So we have a single target magnetron system like this one. This one is a multi-target magnetron sputtering system. This is a low energy ion source, CVD system, and other deposition systems. And then we also have systems that we use to modify surfaces like this one. So this is in high vacuum and in subatmospheric conditions. So recently, we've been developing atmospheric pressure plasma systems as shown here. So we have a jet type, dielectric barrier discharge type systems, where we use this to modify different surfaces from organic and inorganic surfaces. And then we have these are newer systems. So this is again the compact magnetron system. At the center, we have a multi-target magnetron sputtering system. This is also compact. It's just a small one. And on the right, this is a DBD system that we use to modify cotton threads. So we can improve, for example, its dyeability, its wettability, and so on. In the lab also, we have the UP Diliman microfabrication facility. So we have some equipment that can be used to fabricate devices and basic characterization tools. So we have a clean room, or the white room, and the yellow room. We also have our computing system. So this is, I think, around 200 core computing system where we do basic materials modeling, mostly like DFT, MD, and Monte Carlo simulations. More recently, we've been doing computational fluid dynamics for our plasma jet nozzle simulations. Rapid prototyping is also important. So once we have our design, we have the simulated model and so on, then we have our 3D printers where we fabricate our own nozzles and use these nozzles to try in our atmospheric plasma system. So like in this case, so by just varying the width of the channel, we have different effects or different ways of producing the plasma plume, like as shown here. Though maybe in the picture here, maybe it doesn't really show any difference, but in actual operation, there's some difference. So this one is another modification, and because of the rapid prototyping process that we are doing, we can do a lot of iterations of different nozzle designs like these two. And then after that, we have also basic machining tools, and we use this to finalize the nozzles that we have developed for actual application. So in our laboratory, we do a lot of research on device development like PVD or physical vapor deposition, CVD or chemical vapor deposition, low energy ion sources, and atmospheric pressure plasma sources. Most of our work involves either thin films, growing thin films, or modifying surfaces. And in terms of materials, it is also broad from metals to nitrides, oxides, and even polymeric materials. And in terms of applications, we have also varied applications depending on the need of the industry or uh, the the priorities of the our science, our Department of Science and Technology. So let me now shift my talk to plasma. So what is plasma? So if you have these devices, if you are watching this right now, then you might be using a device, or you're using a device that at one point in its process went through a plasma-based process. So why plasma? Because we can get along without computer chips and mobile devices. So in the previous probably how many decades? So in the 1960s, 70s, plasma has been heavily used in the production of integrated circuits. At present, we are diverging or looking at other applications of plasma outside microelectronics. So before, plasma is one of the processes used to fabricate these computer chips or the device. So it's a series of deposit pattern etch and so on. So without plasma, then probably we will not be enjoying integration of our devices. Unlike before, we used to have discrete components, but with plasma, or actually with the use of ion sources or ion beams, we're able to miniaturize and integrate these transistors in a very small area. And that's why we have solid state electronics. Now, aside from that, we have also plasma around us. You may not be aware, but you might be using devices that were enabled by plasma. So plasma and the technologies they enable is pervasive in our everyday lives. No? Each one of us touches or is touched by plasma-enabled technologies. So because of this, we have better quality of life now and improved our economic competitiveness. So here, this is the future of plasma. So again, we are moving away from, well, we're looking at other applications of plasma aside from microelectronics. And this image just gives us a snapshot of what other applications plasma can provide. So plasma is everywhere. It occurs naturally, like the sun or lightning or even the aurora. But what we are interested in are plasmas on Earth. No? We call this terrestrial plasma. So two common examples of this are the neon sign and the incandescent bulb. So what is plasma? So plasma is considered as one state of matter. Usually it's called the fourth state of matter. And this is created by at higher energies as shown here. So you have the different states of matter here. To further illustrate plasma, let's look at this one. So you have a solid, usually the atoms are ordered, but once you start increasing the temperature, for example, then it starts to liquefy. So again, another example is ice. Once you heat ice, it turns to liquid, so it becomes deformable. So the atom arrangement are now there is some separation between these atoms or molecules. And then as you further increase the temperature, the separation becomes longer and you create gas and it becomes compressible and so on. And the further you increase the energy, then you start to separate the electrons from the atoms. And now you create charged particles in the system. So you will have neutrals, you have gases, you have ions, you have electrons, and so on. So it is said that uh, the universe is composed of 99% plasma. And in our laboratory plasmas that we use, we usually assume that it is quasi-neutral. So the plasma is, the overall charge of the discharge is neutral. So comparing now gas and plasma, for gases, conductivity is really low, but for plasma, conductivity in terms of electric conductivity is very high. In plasma also, you have more than one species as compared to gases, which may have only one. Distribution-wise, this is in terms of its energy. Gases follow a Maxwellian distribution. Plasma may follow non-Maxwellian distribution. And then the interaction may be binary for gases, but for plasma, it can be collective and long range, meaning you don't need collisions or actual collisions to have some interactions because of the Coulombic effects between charged particles. So as I mentioned, we are interested in laboratory plasmas, either in vacuum or in atmospheric conditions. So these are some of the devices that we have in our laboratory. So how do we create plasma? So essentially one way of producing plasma is by accelerating an electron and make that electron collide with a neutral atom like argon. So if the kinetic energy of your electron is more than or higher than the ionization energy of the atom like argon, then you have high probability of ejecting another electron from that argon atom. And you create an argon ion. Now, in terms of electrons, electrons can be emitted by a filament. You can do this by heating the filament to thermionic emission and then accelerate. You accelerate the electrons to the away from the filament, and once it collides with a neutral atom, then depending on the energy, then it's possible that the atom can be ionized. So the reason why we want ions, because we can manipulate the charged particles using electric field or magnetic fields. So in this way, you will have more control in terms of the interactions that you want to get from these gas discharges, okay? So if you're interested in the density of your charged particles, then you can solve this Boson's equation, okay? So when we create plasma or ions, there are two things that we have to be aware of. One is the creation of charges. This is the ionization step. And next is the transport of these ions. How do we make now these ions move so that interacts with your material? So in general, if you have a plasma, then you have your neutral gases or neutral particles. You may have some excited gas particles. They are not ionized, but they're just in the excited state. Some gas particles may be ionized, and you have your electrons. Okay. Now, when we classify plasma, there are two ways to classify this, either in excitation mode or in terms of its thermodynamic properties. In excitation mode, if you're familiar with plasma, you can create gas discharges either using direct current or alternating current. So for DC, you can create a good glow discharge. If the potential is so high, then you might create some arcs or corona. And another configuration that is also of interest is hollow cathode discharges. If you have alternating current, then you can use dielectric materials like the dielectric barrier discharge to produce the discharge. And then you can have high frequencies to produce the plasma. Now, between DC and AC, in DC, you have limitations in terms of the use of electrodes because they should be conductive. Unlike alternating current, you can use different materials from conductive to non-conductive materials. For direct current, usually it's low energy. The plasma is low energy, but the plasma is low density but high energy. Unlike in alternating current excited plasma, the density is high, but the energy is relatively low. Now, another classification of plasma is in terms of its temperature. No? So this graph here shows at low pressure, you have the separation of electron temperature and gas temperature. At low pressures, usually the electron temperature is relatively high compared to neutral gas temperature. Now, as you start increasing your pressure, this difference becomes smaller. And once it reaches near atmospheric conditions, then TE and TG are almost the same. And that's the beauty of using plasma, because you have this broad energy range that you can use to modify different surfaces or materials. So the first part is what we call the non-equilibrium or low temperature plasma, or we call this the non-thermal plasma, or sometimes also called as cold plasma. So this is typically in terms of glow discharges, corona, and even DBD. So the gas temperature and ion temperature are usually near room temp, while electron temperature is somewhere around 10 to the 4 Kelvin or 1 eV. So these are examples of non-equilibrium low temperature plasma. So this is heavily used in the industry. So this is used for thin film deposition, this is used for surface modification, and so on. Now, the second type of plasma is equilibrium air, moderate temperature plasmas or thermal plasmas. This is where you have extreme or hot arc discharges. And here, the gas temperature, ion temperature, and electron temperatures are equal. So you find this in, for example, welding or plasma cutters, and even in plasma gasifiers. So the temperatures here are in the thousands of Kelvin. Now, the third type is the equilibrium high temperature plasma. This is where thermonuclear fusion happens, and everything is in equilibrium and very high temperature. That's 10 to the 6 Kelvin. So this is the plasmas generated in the fusion reactor, for example. So they try to get temperatures similar to the temperatures on the surface of the sun. So comparing now high and low temperature plasmas, at high temp, you achieve close to full ionization. That means all of your gas particles are ionized. While in the low temperature or cold plasma, you have partial ionization. And usually this ionization is really low, especially at low pressure or vacuum. In terms of neutral collisions, it's rare for high temperature because most of them are now ionized as compared to low temperature plasmas. And plasma waves are not observed in low temperature plasmas because it is damped by collisions, the particle-particle collisions. And surface boundaries, of course, in low temperature plasmas, we confine them in chambers. So there's a lot of surface interactions with your charges and so on. So these are some of the important equations that you need to know and understand in order to study plasma and gas discharges. Okay, and in order for you to sustain the plasma, you have to also understand Townsend discharge. So here, even if you create charges here, the sustainability, or it's still difficult to sustain plasma. You may create the plasma, but it will just self-extinguish. So you need to increase the potential until you reach uh, the sustaining region of your discharge. So this is where you also produce secondary electrons in your system where it will be used to sustain the discharge. So this is still the same figure. We just rotated this. So you have a critical part here where once you achieve self-sustaining discharge, then you have a glow discharge. But once you further increase the potential, then you will create the arcs or corona. Again, depending on your application, you can stay within the glow discharge region or you can proceed to the arc discharge region. For any plasma physicist or engineer and so on, they also need to understand the importance of sheath. No? So sheaths are created between the discharge and the surface, and it always have that different. You have a region where you have also a different potential. So here, because of the mobility of your electrons, the tendency is the wall is slightly negative, while the discharge is slightly positive. And once the surface is, once you have your electrons, no, you will create that potential, the sheath potential, where your positive ions are accelerated through that potential. Also, you need to understand Paschen's law, where this is the minimum voltage needed in order to break down your gas. No? So depending on the pressure, depending on the gap between your electrodes, then you can have an idea how much voltage is needed to create your plasma or discharge. So those are some of the things. No? So the plasma is a really complex system, so you need a lot of understanding, and you have to look at different equations in order to solve this plasma problem. Now, let me go to plasma surface interactions, because this is really the topic of this talk. So once plasma is interacting with a surface, then there are two things that really happen. One is that the plasma interacts with the surface or the material, and the plasma is sort of contaminated, because you will have particles and charges coming from the material surface. Again, depending on the application that you want, then you can take advantage of this effect. In addition, the surfaces are also degraded or enhanced due to the heat and momentum flux of particles coming from the plasma. So plasma charges, plasma species interact with your surface, and again, depending on the goal of your interaction or the interaction, you can degrade the surface such as etching, or you can enhance it such as functionalization or growing a thin film. So again, it depends on your goal. No? So these are just some of the interactions of your plasma with a surface. So you can have reflected particles, you can have sputtered particles, or you can have implanted particles below the surface of below the surface. And aside from that, you also have other effects. You can induce different effects on the surface. So here, so again, we are looking now at energy, the particle coming from the plasma and how that particle interacts with the surface. So once a particle is incident, a particle that is incident on the surface, it carries an energy. So depending on the energy, you have different interactions. In the lower energy regime, as shown here, most of the interactions will be because of the low energy, then most of the interactions will be the particle is deposited on the surface of your material. So this is used when you want to grow a film. So you have to control the energy such that it will not be reflected or it will not create damage on the substrate surface. So you want the right energy for the particle to be deposited on the surface. Now, at a relatively higher energy regime, like this one, you are now removing particles from the surface. So this is sputtering, or it can be etching. So you're removing particles from the surface, and you can use that, let's say, you can use that to deposit on another surface. And if you further increase the energy, then you have what we call now implantation. So this is also important, especially in the microelectronics industry, because you want to modify the electronic properties of your substrate. Now, recently, there has been work on low energy implantation. So if you look at this graph, we are now looking at sub 1 kV implant energies for ultra shallow junction formation. So as you can see, as the energy increases, the flux starts to decrease. So you have more flux at particle flux. You have more particles coming or arriving at the surface at lower energies. In terms of energy distribution, plasma follows this distribution, Maxwellian type, and you always have this high energy tail of the plasma. The population may be small, but sometimes the effect of this high energy ions or atoms can be detrimental to your process, like if you're developing a device. So sometimes you can narrow down the energy distribution by extracting the ions, and you produce an ion beam. So with ion beams, you have a narrower energy distribution, which allows you to have more control of your process. So in our work, we actually use weakly ionized plasma, low temperature plasmas. And for us to produce this plasma, it should be electrically driven. So either using DC or RF. And then because it is weakly ionized, then you have more charged particle collisions with neutrals. And this is where different effects are induced through these collisions. Surface losses are also important at the boundaries, and plasma is sustained due to ionization of your neutrals. And as I mentioned earlier, electrons and ions are not in thermal equilibrium. So it is this type of plasma that we use for different material processes such as sputtering and deposition, surface modification, and can be used as ion reservoir for ion sources. So this is the energy density map of our plasma. So we usually have somewhere here, our laboratory plasmas and industrial plasma. So it's still relatively low energy, as you can see, and the density is around 10 to the 10 per cubic centimeter. Now let's look at applications. So plasma has been used for surface engineering. So this can be in films such as coating on a surface or modifying the surface. In surface modification, you can induce physical effects or chemical effects. So talking about thin films, so essentially you are putting another layer of material on a surface. So depending on the target application, you can control different film properties like its wear resistance, chemical inertness, thermal stability, friction reduction, and other properties such as optoelectronics. So that's for the film. But it's also important for you to understand the interface between the substrate and the coating. So this is where you should improve or you should have good addition between the film and the substrate, as well as less strain or more less mismatch between the film and the substrate. Sometimes the surface are also important, so you can control the smoothness or the roughness of the surface of the coating. And finally, the substrate. So it is important to understand what type of material your substrate is, the geometry, as well as its other properties, mostly mechanical properties. So where do we find applications of thin films? So aside from microelectronics, we use them also for optics, like optical coatings. This one is hard coating. So this is your drill bits, your cutting tools, and so on. You can have functional films. It can act as a barrier. It can act as a catalytic material, and so on. Thin films are also used for implants, no? Because there are some implant materials that are less compatible with bodies, no, or living things. So we coat the surface with a compatible coating. And lastly, here we have the application of coating as aesthetic coating. So, for example, if you want to produce gold color, then you can have your this material coated with gold. So this is an example of cutting tool. So you have this cutting tool. So if it's coated, this is coated. When the tool is uncoated, after some time, because of the poor heat dissipation, you have debris accumulating on the edge. And this makes the precision cut less precise. No? And eventually, because of the inefficient dissipation of heat, then eventually the material will break or fail. But with coating, so you have to choose the right coating, then it can dissipate heat easily, as well as have low coefficient of friction. So you will have a smooth cut, and that means that with coated materials or coated tools, you can increase the lifetime of your tools, and that's where coating becomes important. So one of the major processes used in coating or growing thin films is by sputter deposition. In this way, if you can imagine billiards, no? Playing billiards. So once the cue ball hits this billiard balls, then they will just scatter. So the same principle is used in sputtering. So you have, let's say, an atom accelerated to the surface of a target, and depending on the energy, if the energy is too high, then it is able to remove particles from the surface. So you have here the sputtering process. So in our lab, we've been developing aesthetic coatings or aesthetic and protective coatings. So what we want to do is to try to mimic or produce gold coated tools or surfaces. And if you're familiar with titanium nitride is actually color gold. But still, you need to tune certain process parameters such that the color is similar to gold. And we were able to test this. It's really close to the natural gold color. Aside from that, because it's titanium nitride, then it has also good anti-corrosion properties, at least with this test. We did a salt spray test and with chloride, because one of the interested users of this technology are uh, companies or, let's say, resorts, that are located along the beach. So they have a really big problem. They have a problem in corrosion because they are near the sea. And we have also tested its adhesion properties. So we have really good adhesion between the surface and the substrate. Also abrasion, it's not really abraded. So here's a demonstration just using a steel wool. And we can see that if we try to scratch the surface, we actually did not scratch or created any scratches on the surface. In fact, it was the steel wool that was damaged during this test. So these are some of the coating colors that we have produced. So aside from gold, we tried gross gold on the further letters. I think we don't have a name for this, but it has a bluish, purple bluish hue. And that means that by tuning the different operating parameters of these of our deposition process, then we can create different colors. We've done also diamond-like carbon coatings. So this is an example of a DLC coated drill bit. And we successfully deposited DLC and improved its hardness. So we tested its hardness in terms of the number of holes that they can produce. And we were able to more than double the number of holes when the tool is coated with DLC. So this one is just a basic scalpel blade. So we just want to test if we can sustain or maintain the sharpness of the blades, but once we coated this, because again, the coating can protect the blades from harsh conditions. Although we know that this is disposable, but we just want to demonstrate that if you coat the scalpel blades, then there's no change in its sharpness, but you can improve its anti-corrosion properties. So we did the test on pig skin, and we actually have no difference in terms of its sharpness. But we improve its hardness, we improve its anti-corrosion properties, and so on. We also have catalytic thin films. We actually use this for wastewater degradation. So these are titanium dioxide-based catalysts, and we use this to degrade organic matter in aqueous solutions. This one is an oil-water separation membrane. So we deposit different materials on the mesh and use this to separate oil and water. So the good thing about this material also is that it has self-cleaning properties. So if we expose this to white light, then we can remove any residual oil on the mesh. We also did some initial work on energy harvesters. These are piezoelectric zinc oxide films, and we want to use this as an energy harvester. So it's vibrational. Although we try to, because it still operates in high frequencies, we're improving this to and shift it to detect lower frequencies. Now, let me now go to surface modification because, again, this is also very important to us. So when you have a surface exposed to plasma, you have different interactions. And as mentioned earlier, it can be physical or chemical interactions. So one major application of surface modification is functionalization. So essentially, you're just attaching a functional group on the surface of a material. And depending on that functional group, you can induce, for example, make it hydrophobic or hydrophilic. So functionalization is limited to a few angstroms. And this is good for heat-sensitive materials because remember, we are using cold plasma here. And then three-dimensional objects can be treated without any difficulty. And it's easy for us to integrate this in a processing line. So one major drawback of functionalization is its aging effect. So that means that after some time, for hydrophilic materials or for hydrophobic materials, after some time, it can go back to its hydrophobic property. So if this happens, then you can use this immediately after treatment or improve the cross-linking treatment properties of your discharge, or just store it in a low temperature or polar solvent. Because again, your functional groups might migrate, or there might be some rearrangement on the surface that makes it more hydro, or go back to its hydrophobic property. So here's an example. So this is a rice husk. No? So rice husk is just a waste, and we want to use or extract rice husk from nanosilica. And in order for us to use the nanosilica, we treat the nanosilica with plasma. So we're able to functionalize the nanosilica with mostly silane groups and improve its compatibility with epoxy. So we use nanosilica modified nanosilica in epoxy resin. Another important application of surface modification is grafting. So it's a two-step process. First is you functionalize the surface, and then you rely on conventional chemistry to improve the addition or attachment of a functional group. With grafting, you remove the dependence, or decrease the time-dependent aging effect on polymeric materials. So that means for grafting, the effect is more long-term. So here's an example also of our work on grafting acrylic acid on PTFE. So this graph, as shown here, if you only treat your surface, then after 1 day or within 24 hours, you will now notice the hydrophobic recovery. And over time, after 7 days, then you slightly increase the hydrophobic nature of your surface. Now, unlike plasma-treated and grafted PTFE, as you can see here, in terms of its contact angle, the contact angle is almost constant, or the surface energy here is almost constant. So we're able to show that there was grafting on the surface of acrylic acid. So one application of this is really for biomaterials. Then we also have polymerization. So polymerization is more permanent, and it's really thicker compared to functionalization and grafting. So this can be thin, pinhole-free films, and it is you can vary the structure or composition of your polymer films. So depending on the monomer that you're using, you can achieve chemical inertness, pinhole-free films. You can use these on various substrates. Thickness is variable. It can be from nanometers to micron thick films. And of course, you can have multi-layers or multi-layered films. So aging also is not a problem because the film is really near its bulk property, so there will be no more change in terms of rearrangement of the functional groups on the surface. Well, another consequence or important thing that you can do with plasma polymerization is that you can actually create a new plasma polymerized film. So if you have a precursor, you can fragment this precursor and use that to form another type of film or another type of layer, and you can produce different moieties as compared to the conventional polymers that you usually make, out of these precursors. But there will be a lot of tuning of the different parameters. You have to understand how these monomers are fragmented and so on. So we did this before. We deposited polyaniline on the surface of ITO and glass substrates. So one of my students actually designed this basic CVD system. He introduced the aniline and he was able to form the film. So this is the film. So to know more, you can check our publication on this research. Now, another motivation for us on why we want to use plasma modification or plasma-based modification is for polymeric materials, especially biopolymers. For natural polymers, processability is a very big issue. No? So not all natural polymers can be dissolved in solvents, and it's very difficult to dissolve this. So what we want to do is improve its dissolution by treating with plasma. So here's an example. This is cellulose, and we were able to improve the dissolution of cellulose when we pre-treat the cellulose with plasma. So cellulose is a candidate material for food packaging. Another ongoing work that we have that we're doing now is kappa carrageenan and alginate. So these are again natural materials, and we want to modify them for processability. Before, it's difficult to process this because of its high viscosity, but once we pre-treat the material, viscosity now is controllable, and that means processability is also controllable. So we also have this chitosan composites. Application is for biomedicine. We also have the hydrogels. So this is used also for wound healing. This is also ongoing work. We also have hydrogels again, but this one for agriculture, and we want to use this for soil conditioning. So we have started also plasma agriculture, but again, we are still in the initial stages. So we want to continue working on this. Then another important project that we're doing now is modifying bamboo, because bamboo is poised to be an important material for the construction and furniture industry. So we want to create laminates instead of scrimber, because scrimber has a lot of steps. For laminates, we want to create layers of bamboo. The problem is addition of bamboo and fire retardancy. So one of my students developed this plasma system, and we want to improve the addition of bamboo and also improve its fire retardancy. So first, we modify the bamboo, make it more hydrophilic, like this one, and improve its addition strength up to 55%. Now, take note, we're using polyvinyl acetate because right now we cannot use formaldehyde-based adhesives. And this is the result. So we have more or increased addition strength for plasma treated bamboo. This one is the fire retardancy test, and we are also able to improve the fire retardancy of bamboo after plasma treatment. So as you can see here, you don't see any flame even after 90 minutes. But before, if it's untreated, you will see flames or ignition even after 30 seconds. So that's the effect of plasma treatment. So hopefully we will have this type of structure, the laminates. So this is still also ongoing right now. Sorry. This is a coconut coir. So we have an industry partner who wants to improve the quality of coir or find other uses of coconut coir. So what we did is we make the coir hydrophobic, and as shown here, and we can use this as cement reinforcement. So we're able to improve, I think, 50% the compressive strength of cement. This one also is graphene, and we also use graphene, plasma treated graphene, to improve the strength of cement. So this one is plasma induced reduction. So we can use plasma to form metallic nanoparticles such as silver, and we use this to couple with titanium dioxide. And we use this as a catalyst. This one is plasma treatment of TFT, and we're able to use this to improve the switching capability of TFTs. And you can also use this also to tune the Fermi level of your TFT or the material. I think here this is IZO. So this one is the nanoparticles that I mentioned earlier. So we embed this in nanofibers and use this as a photocatalyst. And we can improve, using plasma treatment, improve the degradation of organic dyes. Okay, this one is a recent work. We also did some molecular dynamic study to determine the etch tap mechanism in plasma enhanced atomic layer etching of silicon nitride. So there's still a lot of challenges in plasma system design because of the complexity of plasma. There is a large length scale and a large time scale that you have to take note of. So that's why we want to develop predictive modeling and evidence-based decision-making to improve our plasma systems. So right now, there's also a drive for using data-driven design because, again, modeling alone is not enough to improve your plasma designs. Now, our research will not be possible without the collaboration of these different institutions, local and international, these different societies, and of course, our collaborators. So to summarize, so plasma treatment is capable of modifying surfaces physically or chemically. And the good thing about plasma is that you can use solvent-free methods beyond conventional wet chemistry. From our experience, plasma surface engineering is reliable, reproducible, mostly inexpensive, maybe energy efficient, and can process complex geometries. So we also see that plasma-based processes, especially atmospheric pressure processes have high potential for scalability. So to summarize, to accelerate the development, the community of plasma and material scientists and engineers should work collectively to realize the potential of these technologies to meet the needs of the present without compromising the ability of future generations to meet their own needs. So I would like to acknowledge our funding agencies, so both local and international, because they're very helpful in continuing our research. They're very supportive. And with that, this ends my presentation. Thank you very much.
Thank you very much, Professor Magdaleno Vasquez from the University of the Philippines in Diliman. Yeah,
Yes.
well, now it's time for the questions from the panelists first, and then from the Magdaleno Vasquez por su interesante charla. Ahora es momento de pasar a las preguntas. Primero de las preguntas primero de los panelistas y, y el público que nos sigue puede dejar sus preguntas inmediatamente. Al final lo leeremos desde las páginas. Perfecto. Entonces, empezamos con las preguntas. Isaías Gonzalo Oliveira, from the Federal Rural University of Rio de Janeiro.
Hola, good morning, everyone. I don't have a question, only thanks the speaker. Thank you very much.
Thank you very much.
Okay, Professor Isaías Gonzalo Oliveira from the Federal Rural University of Rio de Janeiro in Brazil. Well, from Nantes in France, Julio Guzmán. Julio.
Hello.
Hello.
Hello, thank you for your presentation, sir. I just have a small question regarding,
Yes.
I don't have the slide number, but you were showing a plot where, during your talk, you were saying that, you always have a kinetic energy distribution of your plasma, and depending on the application, sometimes these high energy tails might be even detrimental for whatever process you're planning to perform. So I was wondering, I'm not in the field, so I was wondering about the different possibilities for selecting, narrowing down this energy distribution. I was wondering specifically about, maybe it is a naive question, but what about using magnetic fields? Given that, and I don't know, ions with different kinetic energies might deviate differently depending on the energy with respect to a magnetic field. So is it possible to play somehow in order to narrow down the distribution, either by I don't know, somehow some sort of thermalization of the high energy tails, or just by cutting them out? Is it possible?
Yes, thank you very much for your question. You are very correct in terms of controlling the ion energy. So you can use, usually we use electric fields to filter. So we can create what we call an energy filter to remove the high energy components. They can be diverted or they can be trapped in a high magnetic field. I've done that actually because I tried to extract, let me see, where is that? I tried to extract low energy ions. So when I talk about low energy ions, we are talking really low, like in the hundreds of EV. So that's relatively low. So I use mesh, and in the mesh, I apply an electric field. So all the ions are accelerated downstream with more or less the same energy. So we call that monoenergetic ions. Although it's very difficult to control because, again, you will have some stray energetic neutrals. The energetic neutrals are difficult to control, of course, because they don't have any charge. So if they are energetic in the first place, then they will just go through your electric mesh or your what do you call this, your magnetic field. So that is done in producing ion beams for ion implantation. So they just accelerate the ions to certain energies depending on the implant energy that you want. So yes, that's one technique that is usually done to control the ion energies. But for neutrals, maybe it's difficult to, difficult to control.
Okay, thank you very much.
Thank you for your question.
Thank you very much, Julio Guzman from Nantes in France. Well, now it is, let's move to Chile. Professor Felipe Mundaca from the San Sebastián University in Puerto Montt, Chile.
Hola, hello.
Hello, yes.
Thanks for your lecture.
Thank you.
I only one question, and in your last slide, you showed us one paper about photocatalysis. Can you tell us about your result in this paper? Well, I ask you because I work in photocatalysis.
Okay, so here we have titanium dioxide. So usually TiO2 is active in the UV region, ultraviolet. So our goal for this research is to make it active in the visible light region. So in order to improve or shift the activity of TiO2 to the visible region, usually you couple this with noble metals such as silver. So here we have silver. So in our process, we put silver nitrate, or we put the TiO2 in silver nitrate, and the silver ions will go to the TiO2, but they are still in as an ion. So we treat this with plasma to reduce Ag plus to metallic silver. So if you can see here in the TEM, we have small particles of silver, and we actually use this also. We use Raman to also verify the presence of Ag, because Ag, if it's in a nanoparticle, has plasmonic properties. So it actually enhances the signals of TiO2. So once we have this Ag TiO2 nanoparticles, we put them in the, we embed them in the nanofibers, and we expose this to plasma so that some of the particles will be exposed on the fibers, and then we use visible light to degrade test analyte like methylene blue. So we're able to show how the silver and TiO2 can be coupled together and form a visible light active nanoparticle. So we're able to achieve that.
Okay.
So I think I have
titanium dioxide is anatase or rutyl structure.
It's anatase, yes, anatase.
Okay. And well, I think you measure also the conduction and valence band position, no? With respect to
the band gap.
Yeah, or not?
Yeah, we did measure the band gap. I don't have the actual data here, but it's once we have the silver, it's shifted to visible light. I think it's just below 3 EV. So maybe 2.8, 2.7. I have to check, but because TiO2 is around 3.3, 3.0 to 3.3, right?
Yeah.
EV. So with the silver, and depending on the amount of silver that you put, then you can actually make the couple, we call that Janus structure. So the Janus structure, or the silver and titanium dioxide, becomes visible light active. So that's why we're able to degrade, for example, methylene blue using visible light instead of UV. So here, for example, we are using a solar simulator to degrade the methylene blue. But this one is titanium, for this one, this is copper oxide and TiO2. For this one, it's silver and TiO2. Let me go back.
Okay. Well, this is my question. Thanks for your lecture.
Thank you
Bye.
very much.
Thanks, Luis.
Okay, thank you very much, Professor Felipe Mundaca from San Sebastián University in Puerto Montt, Chile. Now let's move to London or to Cambridge with Professor Stuart Holmes. Professor Stuart Holmes.
Magdaleno, thank you for your very comprehensive presentation on plasmas there. Very interesting. Thank you. I have some small technical questions. You mentioned the effect on the silicon device. I think it was silicon. Presumably, you tune the Fermi energy because you're perhaps changing the surface. Do you get any doping effect? Can the plasma create any doping effect in semiconductors?
Depending on the incident energy, you may have some doping, or you can just simply etch the surface, depending on the energy. Although doping might be very difficult at lower plasma temperatures or low or cold plasma, you can maybe dope it if you apply a bias so that you really accelerate the ions and go inside the surface. But most of the time, it will just affect the surface either by deposition or by ablation or etching the surface. And we have done that. It's also ongoing. So for example, nitriding. So you want to put nitrogen into the stainless steel, for example, because you want to harden it.
Yeah.
So if we just use plasma without any biasing on the substrate, then it's very difficult to nitride it. But once you apply a bias, depending on the bias, usually it's a highly a negative potential. So the nitrogen ions are really attracted and embedded on the surface. But you will create that gradient. There's a concentration gradient. Of course, at the surface or near the surface, you have higher concentration as compared to the deeper parts of the material. But in this case, we don't expect any doping because the plasma is just cold plasma.
Yeah. Thank you. You also mentioned that adding your bamboo into some materials makes the material stronger. Does the process make the bamboo stronger? If you have a bamboo structure, does the strength of that change in some way, the mechanical properties?
Actually, if I'm not sure if you can see in this image, we actually have the adhesion is much stronger than the bamboo. So you will see here some fibers already being removed. So in this case, we were able to improve the adhesion between the interface or between the bamboo and the adhesive. But at the same time, the strength now is determined by the bamboo strength.
Right.
So our major concern here actually is that the vendor cannot tell us the exact age of the bamboo. So because this is just like outside and then you just get it and then we just prepare it. But in terms of modifying the properties, the modification may just be surface and maybe subsurface. So if you look at this one, so this one, we're able to modify the surface,
Yeah.
right? So here there's no flame, but we have ember below.
Yeah.
So because you are still heating, it heats up. So the high heat makes the, let's say, it's like carbonized the inner surface of the bamboo. But
Yeah.
on the surface, I think it's effective in terms of preventing the flame.
Yeah. Yeah. It's a
So-
good demonstration. It's a good demonstration.
Thank you. So
Thank you.
I
I have
think
one
that-
further comment. You mentioned
go
you use in your introduction density functional theory. What
Mhm.
what aspect would you use of this work? Would you use density functional theory for?
So, well, our collaborator, they're working on 2D materials.
Oh, I see.
Actually, our goal is to modify these 2D materials like graphene
Yes.
using plasma like oxygen ions and so on.
Yeah.
So,
Okay, so that's where it's coming.
yes. So we actually had that small computing cluster for the simulations.
That's good. Thank you for your answers to my questions, and thank you again for such a very comprehensive talk. Thank you.
Yes, thank you very much.
Thank you.
Thank you, Professor Stuart Holmes from UK. Well, let's check now if there is a question from the public. If from Peru there is no questions, according to Melvin. And let's check from Colombia or from the social media. Are there any questions in Colombia from University of Bogotá in Colombia? University of Colombia in Bogotá. Ximena Velázquez.
Professor Luis, good morning, Professor. No, we don't have any question from here, from our university. Only the people say that thank you for an interesting talk. Thank you,
Thank
Professor.
you very much.
Mhm. Okay, thank you very much. Well, we have finished with the question, Magdaleno Vasquez. Well, do you want to say goodbye words, maybe?
Mhm. I'm
Would you?
sorry.
Would you like to say any goodbye words? To
Yes,
say goodbye?
Again, thank you very much for having me, and I hope we're able to share some of our work and hopefully also inspire others to look at. In our case, we look at just the concerns around us, like our products and so on, and improve the quality of these products. So like bamboo or the biopolymers. So we're working on cellulose, chitosan, and now hopefully we will start with starch as well. And we use this technology like plasma to improve certain qualities that can be used in other important applications, especially in bioplastics. So thank you very much, and I hope to share again in the future if we have time or opportunity.
You are welcome to attend many times. Every Saturday we gather at this time. I understand that now you are in Japan in this moment.
Mhm.
That is very late, right? But
Yeah.
you are welcome to attend many times. But when are you planning to go back to the Philippines?
Tomorrow.
Tomorrow go back to.
Yes.
Okay, extend my greetings to all the friends in the University of the Philippines,
Yes.
please,
Yes.
because since the last time I visited there, when our deceased friend Professor Henry Ramos, who is the pioneer there in the Philippines
Yes.
about plasma, right? Well, the plasma research there in the Philippines, I think it is very developed rather than in the most Latin American countries. I think so. I haven't heard that Latin American countries has developed so much as in the Philippines. Well, thank you very much, Magdaleno. You can stop sharing your screen because we want to say goodbye to you by now. Please open your cameras, the rest. Abran sus cámaras el resto, por favor. Open your cameras and your microphones to say goodbye to Professor Magdaleno Vasquez. Okay, your microphones as well, sus micrófonos.
Bye.
Bye.
Hasta
Bye.
luego a
Thank you,
todos.
and
Que estén
goodbye.
bien.
Bye. Thank you. Thank you.